So there's one other special force that we'll come back and talk about how much work it does, and that's the spring force. And so we haven't talked about the spring force yet, so let's introduce it first as a force, and then we'll come back and talk about how much work is done by a spring. So you'll notice I've set up a situation here where I've got a spring attached on one side to a wall, and on the other side I've put some mass. Where the mass sits, right, so the place that it just sits and that's where it'll stay is known as the equilibrium position. It'll sit there, the mass will sit there because equilibrium happens to be the position where the net force is zero. Now if I start moving the mass away from equilibrium, so notice here's a situation where I'm exerting an external force pulling this mass to the right. There's a spring force that's pulling it back to the left. As I pull harder, I need to exert a larger force. There's a larger force from the spring, right? So one of the things this tells us is that the farther the spring is pulled away from equilibrium, the larger the force is that's exerted by the spring. So if you're not very far from equilibrium, the spring doesn't exert a very large force. As you get farther and farther away, the spring force gets larger and larger. We can quantify how this works by what's known as Hooke's law. So Hooke's law basically tells us that the magnitude of the spring force, so the magnitude of the force exerted by the spring on the mass trying to pull it back towards equilibrium, can be calculated by K, and K here, this is little k, it's known as the spring constant. And the spring constant is just a measure of the stiffness of the spring. So if you have a very large K value, that means you have a very stiff spring. If you've got a small K value, that's a weak spring. But I can take K and multiply it by delta L, where delta L is just this distance that the spring is stretched or compressed. And since this is a magnitude of a force, I know it has to be positive. K here is always positive, and delta L we've set up to be a positive distance. So it doesn't matter whether I stretch the spring to the right or compress the spring to the left. In either case, I'm going to go ahead and use delta L as a positive distance. Okay? Now what you do notice is that when I actually push the spring, so I exert a force that pushes this mass to the left and that compresses the spring, well, now the spring force, its direction turns around. So again, as I pulled the mass out to the right, the spring force pointed to the left. As I push the mass to the left, the spring force now points to the right. So again, what we can take away from this is that the spring force always points back towards equilibrium. This is what's known as a restoring force. So if your mass starts at equilibrium and you pull it a little ways out to the right, the spring forces point to the left. If you push the mass a little bit to the left, the spring force is going to point back to the right. So spring force always points towards equilibrium. And so again, we can take advantage of this direction and put together a vector statement that says that the spring force as a vector is equal to negative, here's our positive value of K again, there's our spring constant, times x. And x as a vector here is a displacement from equilibrium. So it basically says how far have you pushed it, but now it does care about the positive or negative direction. So if you displace your spring to the right, this minus sign says that the spring force will point to the left. If you displace your spring away from equilibrium to the left, the spring force is going to point back to the right. So what this minus sign is telling you is that the spring force always points in the opposite direction of the displacement. That's how the spring force is always able to point back towards equilibrium. All right, so this is the spring as a force, talking about the elastic force. Well, what if we wanted to talk about the work done by a spring? So again, our inclination might be to say, oh, well, we know how to calculate the work done by a force. It's given by this expression. So the work done by a spring is going to be the magnitude of the force times the magnitude of the displacement times the cosine of the angle between those two vectors. But the problem here is that the spring force is not constant, which means we can't use that equation. Right? We said this equation was only valid for constant forces. Spring force isn't constant. Again, you pull it away a little bit, I've got a relatively small force. You pull the mass a large distance away from equilibrium, I've got a pretty large spring force that's trying to pull it back. So the spring force isn't constant, I can't calculate it this way. Well, in fact, it comes from calculus, right? But I can get the equation to calculate the work done by a spring, and it's given by this expression. So here's a negative sign out front, 1/2, again there's K, my spring constant, and now this is the final displacement from equilibrium squared minus the initial displacement from equilibrium squared. So if this was, in my picture, my initial position, right, so my initial displacement from equilibrium, and then I move the spring out further, so here's my final displacement from equilibrium, I could plug in those two values, square them both, and calculate the work done by the spring. Now again, one thing that we can't forget is sitting right there. Right? So this negative sign out front is actually really important, because I know that in this case I've pulled the spring, so in my picture here, I've pulled the spring farther away from equilibrium, even though the spring force was always trying to pull it back towards equilibrium, which means that the spring force points in the opposite direction as the displacement. So I know that the spring has done negative work in this case. Well, if my final displacement is larger than my initial displacement, then this inside the parentheses is going to be a positive quantity. So I need this minus sign here to give me the right sign for my work value. Because fundamentally what I know is the spring is going to do positive work as a mass moves towards equilibrium. So when you release this spring and it moves back towards equilibrium, that's because the spring force is doing positive work, because it always points towards equilibrium. As it moves towards equilibrium, that means the final displacement is smaller than the initial displacement. This would be negative, and again I need this negative out front to make the work term be positive. On the other hand, if I pull my mass away from equilibrium, the spring's going to do negative work under those conditions, because again the spring force points back towards equilibrium, I'm moving the mass away, so force and displacement point in opposite directions. So here's the equation that we're going to be able to use to calculate the work done by the spring, and here fundamentally is the check we're going to use to make sure that we've got the right sign when we do that calculation.